Good afternoon. We're trying out a Year 12 lesson on exponentials and logs reducing to linear form. So the idea is we're going to take an equation of the form y equals a times x to the power n, so an exponential growth equation, and look to rewrite it like a straight line graph. So our first example says we've got two variables d and r, and we've got a table of values for d, 2, 3, 6, 8 and 10, and values for r. It says it is expected that the relationship between r and d may be of the form r equals k d to the n, where k and n are constants. So there's our table of values. What we're going to do is take logs of both sides of the equation. So I'm going to write log r, and it doesn't matter what the base is at the moment, equals log of all k d to the n. We're going to use our rules of logs to split this up, and this is where our straight line equation is going to come into it. Be aware that the n is only a power of the d, not of the k. So when I split it up, I get log k plus log of d to the power n, and what I can do with the power, I can bring it down the front of this term here. So we end up with log r equals log of k plus n log d. Now, if I plot log r against log d, log r being the y and log d being the x, we get this, where the log k is our constant of a straight line graph and the n is the gradient. So looking back to the question again, part B says complete the table of values and then let's look to draw the graph of it. So log d against log r, I've actually already done, if you like Blue Peter, here's one I did earlier, like that. So I've got my values for log d, values for log r. I've chosen log to the base 10. It doesn't matter what base you choose as long as you're consistent with it later on. So there's my table of values. What I've done, just the top half here, is plot it. So I've got all my log d values, log r values here. I've just done a rough straight line graph. I've got my 1, 2, 3, 4, 5 points, and I've extended the line so I can estimate where the line crosses the y-axis. And as we said before, y equals c plus mx. C, the intercept, is log of k. My intercept here is about minus 1.9. Because I did log to the base 10, how do I find the value of k then? I do 10 to the power minus 1.9, which is a very small decimal, to 2SF, 0.013. We also said that n is the gradient. When you're trying to do the gradient of these things, try and find the extreme values of the line. So in my case, to go from that point at the intercept, minus 1.9, to that point at the top, where the y value was 2.38, all I do for my gradient is the change in y, which is 4.28, divided by the change in x, which in this case is 1. So my gradient n is 4.28. There was then a part D to our example. Use your model to predict the value of the value of D when r is 1000. Well, use your values and just stick it into the equation and solve it. So r equals 1000 equals 0.013 times d to the power 4.28, and then solve it. Undo it, so divide by the 0.013 to get whatever it is. I use the answer button of the calculator, and then if it's d to the power 4.28, I need that root of my answer. Press buttons, and to 3SF, one decimal place, I got about 13.9. And don't forget, the question says use your model, so this answer is correct because it's my model. There won't be an exact value for this because it's based on your estimates for the two constants that you had to find for k and for n. So that's how we do the first one, when it's in that form there. The two forms we've got, y equals ax to the n, is when x is being raised to a power, and the second example we've got is when it's y equals ab to the x, when x is the power itself. Now it might be, in that case there, we have an example like this one, where it says, over a period of time, theta equals k times a to the power t. This a could have been an exponential, so this is an exponential growth. E to a power something, e to a constant is still a constant, so I could have written, I'll choose a different constant rather than that. E to the power m, whatever m is, e to the power m is just a constant. So these are exactly the same type of expression. So the example in the question has got a table of values. T is the time, 2, 4, 6, 8, 10, 12. Theta is temperature, so it's exponential decay, it's cooling. So it starts off at whatever temperature it did when you put the hot water in, and it will cool down towards room temperature over a period of time. It says it is suspected that the relationship between t and theta is of this form: theta equals ka to the power t. Complete the table of values. In this case, it's t against log theta, not log t against log theta. We'll show you why in a moment. Work out the values in the table and plot them and see what happens. So I've got here values of t, worked out values of theta, log theta, sorry, yet again to the base 10, and then I've done a rough plot of those like this. And because it's cooling, we've got to align with a negative gradient. And I plotted my 1, 2, 3, 4, 5, 6. My scale is slightly different than on the sheet. Just to fit it on this half of the board, I've gone in 3, 6, 9, 12 for the times, and then 1.6, 1.7, 1.8, 1.9. And yet again, I can read off, I can estimate the intercept to be about 1.95. I can work out the gradient. It's roughly 0.4 down divided by 12, and that will help us do some calculations later on. There's my setup there. Part B says, show that your graph, the relationship, is equivalent to this log equation. Well, same as before. If I got my theta equals ka to the power t, I could take logs of both sides. So log theta equals log of k times a to the power t, and as before, the power has got nothing to do with the k. So when I split it up, I get log k plus log a to the power t. Yet again, the power I can bring down to the front using the rules of logs, rules of powers, and I get log k plus t log a. And that, yet again, is a straight line graph of that form there. Log theta is my y-axis, log k is the intercept, and in this case t is the x variable. That's why it was t against log theta and not log of it. But in the slight difference is my gradient will be log of a. So when I worked out my gradient, I got log a, which was approximately minus 0.4 over 12. So m will be 10 to the power, minus 0.4 over 12, which is about 0.9. And similarly, I can work out the intercept log k is 1.95, so k will equal 10 to the power 1.95, which is about 90-ish. I hadn't worked it out because I wasn't sure what it was going to be. $89.1. So when I put my water in initially, the temperature of this thing was 89.1 degrees, and it's cooling down at a rate of the 0.9 means at every minute it'll be 0.9 of what it was before. And then it cools down so that after 12 minutes it's gone down to what it was, 36 degrees, and it will head towards room temperature. So it will bottom out at whatever the room temperature is. And here endeth my first ever lesson on YouTube.